Hi, welcome to Send to Print. Today we're designing a fully parametric twist snap bottle in Fusion. It twists shut with a satisfying click while keeping the pattern on the lid perfectly aligned with the bottle. And you can adjust the size, shape, and snap strength just by changing a few parameters. I'll walk you through the mechanism, build it step by step, and show you what I learned from testing the printed versions. And stick around until the end. I'll show you how to add the same mechanism to your own model directly in the slicer in about a minute. So let's jump right in. First, let's define our main dimensions. Go to the Modify panel and select Change Parameters. Click that plus icon to add our first one. Diameter, 45 millimeters. Next, add height for the container and set it to 30 millimeters. All right, now let's get started by sketching the outer profile. Go up to Create Sketch and pick the XY plane. Hit C for the circle tool. Start right from the origin, drag it out, and type in diameter. Draw another circle for the inside diameter. Offset it outward by 1.5 millimeters to define the bottleneck. Then offset it another 2 millimeters for the lid. I'm leaving a little extra material on the lid since we'll be cutting the locking slot into it later. Now, let's create an arc pattern for the outer profile. Start with a construction line. Go to Create and use Mirror to mirror it across the Y-axis. Press D for dimension and set the angle between these two lines to 30 degrees. Under Create, find center point arc. Draw the first curve. Add another construction line, then set the angle to 45 degrees. Apply a tangent constraint here. When all the lines turn black, the sketch is fully constrained. We don't need to draw every curve by hand. Go to Create and choose Circular Pattern. Pattern the arc around the center point with a quantity of 12. Each section spans 30 degrees, so 12 copies complete the full 360 degrees. Nice and clean. To make the profile easier to select later, select all the lines that are not part of the final outline and press X to turn them into construction lines. And that finishes our outer profile. Actually, I've just changed my mind. Instead of using fixed stripes in the sketch, let's make this pattern parametric so we can change it later. Open Change Parameters. Add a new parameter called stripes. Make sure it is set to no units. This parameter controls how many vertical ridges wrap around the container. I'll use 36 for now. Back in the sketch, change the angle to 360 divided by stripes and set the pattern quantity to stripes. Now we can change the entire look of the container by changing a single value in the parameter table. Check for that small lock icon. It means it's fully constrained. Okay, let's finish the sketch and rename it to container. Let's build the lid first. Right-click the root component in the browser and select New Component. Rename it to Lid. Press E, select the lid profiles, and extrude them upward by 10 millimeters. Turn the sketch back on. Press E again, select these two inner profiles, extrude them upward by 8 millimeters, and make sure the operation is set to cut. That leaves us with a 2 millimeter thick top wall. And the lid is done. Now let's build the container body. Create a new component named Container. Press E and select the bottle opening. Extrude it upward by 8 millimeters to create the bottleneck. Then press E again, select the body profiles, and extrude downward using height minus 10 millimeters in the negative direction. The parameter height defines the total model height, so we'll subtract the 10 millimeters already taken up by the lid. Set the operation to join and confirm. The bottom is still open, so press E again. Start from the bottom face and extrude upward by 2 millimeters. Use join to close it. Now, I'm pressing Shift plus N to turn on component color cycling. This doesn't change the material or the final print. It simply gives each component a different display color, making their relationship much easier to see. To get a better look at the model, let's go to the Inspect menu and select Section Analysis. If you don't see anything, just click Flip. Right now, these two parts are just sitting face to face. We'll add the twist snap mechanism later. Before moving on, let's think about print orientation. We'll print the lid upside down, with its top face flat on the build plate, while the bottle body prints upright. To make the bottom look more refined and avoid elephant foot during printing, I'm adding a small chamfer here. Add a small 0.6mm chamfer to the top and bottom edges. With this many stripes, each edge is quite short, so a larger chamfer might make the feature fail. Right now, these two parts are just sitting face to face. Next, we're going to build the actual twist-snap mechanism. Before we go any further, let's see how this twist-snap mechanism actually works. First, we have a radial lug on the base part. During installation, you align this lug with the entry slot. Since the slot is slightly wider, it slides right in. Then, as you rotate, the lug follows a curved path until you hit a tiny bump, a detent. With a little extra force, the plastic flexes just enough to let the lug snap over it. The moment the lug snaps past that point, you'll get clear tactile feedback. That's the click sound we're looking for. Once the lug snaps into the locking zone, there's a much higher hard stop wall right in front of it. This wall is too high to be pressed over with normal force, so the lug can't rotate any further, effectively locking it in place. All right, let's start by creating a sketch on the XY plane. Press P and project the interface between the container and the lid. Hide the container sketch for now. We'll start with the lug. Draw a line from the origin and mirror it across the y-axis. Under Create, choose Center Point Arc. Draw a short arc. Press D and set the distance between the two arcs to 1 millimeter. This defines the height of the lug. Also, set this angle to 30 degrees. Now, everything looks fully defined. Okay, let's finish the sketch and rename it to lug. Back in the container component, extrude the lug profile from a plane 2 millimeters above the sketch. Give it 4 millimeters of height and join it to the body. From the side, you can see the lug would start printing in midair, so it'll need support. To avoid that, add a 1 millimeter chamfer to the top and bottom edges. Now the lug can print cleanly on its own. Next, we'll create a matching groove in the lid. Instead of redrawing it from scratch, here's a shortcut. Use the lug itself as the cutting profile. Let's use the revolve tool. Pick the Z-axis as the revolving center. Set it to full and operation to cut. The lug has room to move now, but it needs an entry slot to get started. Plus, we're still missing the hard stop here and the detent. Create a sketch on the XY plane. Press P and project both the lug and its mating surface. Then press C and draw a circle as the groove profile. Next, we're going to draw the detent. Draw a line from the center to the edge. Then use the center point arc to snap to the center and draw a short arc. Set the detent depth to 0.4 millimeters. I think I'll make that value parametric so the tactile snap is easy to tune later. Open change parameters, add a parameter called detent, and replace the fixed value with this new parameter. Finally, set the detent width to 4 millimeters. Now, let's build the hard stop on the other side. Add a construction line. Draw another center point arc. Constrain the arc endpoint to the root of the lug and also to the circle. Use shortcut D to set this angle to 15. Draw one last line to define the width of the entry slot and set that angle to 45 degrees. Select the lines that are not part of the final profiles and press X to turn them into construction lines. Everything looks fully defined. Okay, let's finish the sketch and rename it to slot. With that sketch ready, We can turn each profile into a functional part of the slot. Hit shortcut E to cut the entry slot. Select this profile. Set the extend type to object. Select this face as the target and set the operation to cut. That creates the entry slot. To add the detent and the hard stop wall, let's hit shortcut E to extrude again. Select the small bump and the end profile. Set the start to object. Select the top face and use join. To get a better look at the twist snap mechanism, let's go to the Inspect menu and select Section Analysis. Pick the XY plane and drag it up. The entry slot, detent, and hard stop are all in place, so the locking geometry is complete. But before we print anything, we need to add some clearance between the moving parts. Let's start with the lug on the container body. Grab the offset face tool or hit shortcut Q and enter -0.1 millimeters. Then hit F for fillet, add a 0.5 millimeters fillet to the lug edges to make it glide easily in that groove. And just like that, our twist snap mechanism is finished. With only one locking point, the lid could pivot around it and all the twisting load would be carried by a single lug. We want support on both sides, but luckily we don't need to model the whole mechanism twice. Let's head up to Create, then Pattern, and grab the Circular Pattern tool. Make sure your object type is set to Features, because we want to grab those specific steps from our timeline. The steps that create the entry slot, the hard stop, and the detent. Pick the Z-axis as your center, and set the quantity to 2. For a lightweight project like this, 2 lugs are plenty. It's clean, symmetrical, and gets the job done. Of course, you could always crank up the quantity in that circular pattern to 3 or 4, but honestly, 2 is just enough. Now let's isolate the lid and add clearance there as well. Press Q, select the mating surface around the bottleneck, and offset it inward by 0.1 millimeters. Let's take another look with the section analysis. Now there's clearance between the lid and the bottle body. Let's assemble the parts so we can test the motion properly. Go to Assemble and choose As-Built Joint. Select the lid and the bottle. Set the motion type to revolute. Choose the center axis. Turn the section analysis back on. Now drag the bottle to see how everything moves. As you rotate, the lug follows the groove until it hits a small bump. With a little extra force, it snaps right over that detent with a satisfying click. Now it's in the locking zone, stopped by a higher wall and locked perfectly into place. With the modeling finished, now we get to my favorite part, the magic of parametric control. This is where all that setup finally pays off. Open the parameter table. Let's start with detent. This one controls how the twist snap clicks into place. If the detent is too low, it'll twist in too easily, but it might be too loose to stay locked. If it's too high, it'll be hard to twist. You might need way too much force, or it might not clear at all. Now let's look at the other parameters. Diameter changes the overall width. Height changes the overall height. Because the lid stays fixed at 10 millimeters, most of that height change happens in the bottle body. The stripes parameter is the interesting one. Lower values create broad petal-like lobes. Higher values create finer vertical ribs. I'll use a smaller set of dimensions for a faster test print. Here's the final print. Let's try the mechanism. Align the lug with the entry slot and rotate. Right here, I'm feeling a bit of resistance. Give it a tiny bit of force, and with a satisfying click, it locks right into place. But listen to this, it rattles. I only added 0.1 millimeters of clearance, and I couldn't find anything wrong with the model. So I printed the exact same model in a different filament. And suddenly, the fit was perfect. Same model, different filament, totally different feel. So materials shrink and flow differently. You may need to tune the clearance for your own printer and filament. I also printed a 5-stripe version, which looks more like a flower. But something strange kept happening. Sometimes the petals lined up perfectly after the click, and sometimes they didn't. So I went back to Fusion to find out why. If this lug enters the intended slot, the lid rotates into perfect alignment. But because the two locking interfaces are directly opposite each other, the same lug can also enter from the other side. With 5 stripes, the lid still locks, but the pedals end up misaligned. It might seem like a tricky problem, but the solution is surprisingly straightforward. Break the symmetry so there's only one way to put the lid on, and the actual edit only takes a few steps. Double-click the circular pattern in the timeline. Instead of distributing the two mechanisms evenly, switch distribution to partial and set the angle to 170 degrees. That changes the angle between the two mechanisms from 180 to 170. We don't want to shift it too far, though, or the lugs won't distribute the load as evenly. Let's check if the alignment works now. Our goal is for this lug to enter here, rotate through the slot, and lock here. So let's line it up with this entry slot. But the problem is, the opposite lug is not lined up with its entry slot. In other words, the entry slot is on the wrong side. Because the lid twists into the joint from the opposite direction, this matching slot needs to be at negative 170 degrees. So, let's go back to the circular pattern. In the selected features, remove the entry slot, extrude. Then create a separate circular pattern for the entry slot. Select that extrude in the timeline and use the Z-axis. Set distribution to partial, and importantly, enter negative 170 degrees. Now let's check the alignment again. The slots are here and here. Notice that the one on the right has moved from here to here. When this lug enters its slot, the lug on the opposite side lines up at exactly the same time. Now both can enter and rotate all the way into the locked position. If you try the other entry slot, one lug can start to enter, but the other lug hits a wall, which is exactly what we want. The opening is still a little generous, though, and with enough force, it might still squeeze in. So for better foolproofing, we should narrow the entry slot so the lid simply can't assemble in the wrong position. Go back to the timeline and edit the slot sketch. Make the entry slot smaller, like change it to 35 degrees. That's just wider than the 30-degree lug, but not wide enough for the lid to slip in from the wrong position. Now, the entry slot is tighter than before. If we check it, these two lugs cannot enter the slots at the same time from the wrong position. But when they rotate to the intended position, both sides line up and lock into place. Here's the updated print. At first glance, it looks almost the same. From this angle, though, you can see the change. The two interfaces aren't directly opposite each other anymore. Let's see if it works. Perfect. Now there's only one valid way to assemble it. This mechanism finally works, but I know rebuilding it from scratch for every new project would be tedious. So I created a twist snap cutter and uploaded it to MakerWorld. Let me quickly show you how to use it. Here I've got a solid elliptical container measuring 60 by 50 by 30 millimeters. Instead of rebuilding the twist snap mechanism from scratch, I'll use the cutter to add it. Let's go back to MakerWorld and customize the cutter to match those dimensions. We'll start with inner diameter. Measure the narrowest part of the cutting surface, then subtract at least 7 millimeters. So 50 minus 7 gives us 43 millimeters, and a slightly smaller value is fine too. Next is detent depth. Think of it as the size of the little speed bump the lug has to cross. Larger means a stronger click and more turning force. I'll keep the default 0.4 millimeters. Outer diameter should match the widest part of the model. Our cross section is 60 by 50, so enter 60 millimeters. Total height is simply the full height of the model, so enter 30 millimeters here. Finally, clearance controls the fit between the moving parts. The default 0.1 millimeters is a good starting point. If the fit is too tight, increase the value slightly. If it's too loose, reduce it down to a minimum of 0.05 millimeters. Okay. It may look like nothing changed. Don't worry, the important geometry is hidden inside. Just download the file and put it to work. Back in the slicer, drag in the STL. Then right-click and choose Split to Objects. The cutter is made of two separate parts, one for cutting the lid and one for cutting the body. These are the two cutter parts. Duplicate your container so you have one for the lid and one for the body. Then group each copy with its corresponding cutter part. Next, align the two objects inside the first group. Right-click and center them along the X direction, then the Y direction. Do the same thing for the second group. Now we can run the Boolean operation. Select the group on the left and set the operation to subtract. Make sure the container is part A and the cutter is part B. Leave Keep Original Models unchecked because we won't need those copies afterward. The lid is done. We'll inspect it after cutting the body. Select the other one and run Subtract again. If the model and cutter are assigned to the wrong sides, simply swap part A and part B. Okay. Finally, flip the lid so its top face sits on the build plate. This also gives us a clear look inside. The locking geometry has been cut correctly. The elliptical bottle now has two matching lugs. Everything looks ready. Send to print. Let's see if it works. All right, both the parametric twist snap bottle and the cutter are free to download on MakerWorld for everyone. And, as usual, channel members get early access to this video, plus a detailed cheat sheet and a behind-the-scenes Fusion file showing how the model was built. Okay, that's all for today. If you found this tutorial helpful, please hit the like button and subscribe for more 3D printing designs. Let me know in the comments what should I model next. Thanks for watching, and I'll see you in the next one.